stable or unstable system? Well, in simple terms, we refer to the power system as being stable when A, the power demands and losses on the system are being adequately supplied by the power being generated. This may include some power being imported from a neighboring utility. B, the frequency is stable and close to its nominal value. This is because power supply and power consumption are equal. C, the voltage is close to its nominal value at all points in the system. D, all of the transmission lines, transformers, generators, and other equipment are working within their rated capacity. Unfortunately, this perfect, steady-state condition rarely lasts for more than a few seconds because the customer load demand is always changing. But these changes in load are relatively small, and moreover, they are usually anticipated according to the time of day and weather conditions. As a result, there is normally sufficient generating capacity online, and with the help of automatic equipment such as turbine governors and voltage regulators, the power supply can be quickly adjusted to meet the load demand. Adjustment of the turbine governor's set point regulates the mechanical energy input to the generator and consequently determines the electrical output. This situation is the same whether the generator is driven by a steam turbine, gas turbine, or a water turbine. It may take several seconds for governor adjustment to achieve the required change in generation, but this is quite adequate for normal minute-to-minute variations in load demand on the system. Similarly, the voltage regulators are relatively slow to adjust the excitation of the generators and so meet the change in demand for reactive power. So even in this steady-state, stable condition, slight changes are always occurring to the flow of real and reactive power along the transmission lines. Consequently, the load angle or power angle is also changing continuously. Now, what is this power angle? Well, in order to transmit power across a transmission line, in this example from bus 1 to bus 2, there must be a phase angle difference between the voltages V1 and V2 at each end. This is due to the inductive reactance XL of the transmission line. The resistance of the conductors is relatively small and is usually neglected in these studies. Let's look at a simple example of a single generator feeding a load through a single transmission line. If we consider the load demand at bus 2 to be at unity power factor, then the current is in phase with V2 as shown here. As this current flows through the transmission line, the inductive reactance produces a voltage drop, IXL, which is 90 degrees out of phase. As a result, the V2 voltage will lag with respect to V1. If the load demand at bus 2 increases, there will be an increase in current flow, so the voltage drop, IXL, increases like this. Consequently, the receiving end voltage, V2, lags further behind V1. The power angle, phi, increases as load increases. The value of the voltage drop, IXL, is approximately equal to V1 sine phi. Dividing this by XL, we can find the current. I equals V1 sine phi divided by XL. As power received is proportional to V2I, the amount of active power transferred along the transmission line is proportional to V1 times V2 sine phi divided by XL. Now let's look at the situation from the point of view of the sending end, that is, this generator, or perhaps several generators feeding the same bus. Normally, the generator is feeding into a very large power system. In order to transfer active power along the line, the voltage at this sending end must be leading that at the receiving end. This is in accordance with our power angle equation. In order to transfer more load along the line, the power angle must be increased by advancing the sending end voltage. This is achieved by increasing the energy input to the rotor. Studying the power angle equation, we can draw several important conclusions. The amount of power that can be transferred along a line can be increased by increasing the voltage. Of course, increasing the voltage implies that the transmission line hardware, insulators, and so on must be upgraded. But it does show one of the reasons why high voltage and extra high voltage is favored for transmission. It also shows why it's important that voltage levels must not be allowed to fall during operation. Another clear factor is the line inductive reactance. By reducing XL, we can increase the power capability of the line. An obvious example of this is when two lines run in parallel between two buses, so reducing the total impedance by half. This allows us to double the capacity of the circuit. But let's look at this other factor again, the power angle phi. This curve shows the transfer capability of the transmission line with relation to the power angle between the voltages at each end. When there is no angular displacement across the line, there will be no power flow. As the power angle increases, so does the load transfer. For example, where the angular displacement between the voltages is 30 degrees, then the power transfer across the line is equal to the sine of 30 degrees, that is 0.5 or 50%. At 90 degrees, the sine of the angle is equal to 1, so the load transfer is now maximum. If the angle increases beyond 90 degrees, then the load transfer begins to fall again because the sine of the angle diminishes. So here is an important conclusion. In order to increase the transfer of power across a transmission line, the power angle must be increased up to a limit of 90 degrees. If the power angle exceeds 90 degrees, then the power transfer will be reduced, and the system will probably fall out of synchronism. For stable operation, the system operator loads the system in such a manner that the load angle across each transmission line is much lower than 90 degrees. Let's look at a simple example. Here, the line is operating at approximately 40% capacity. The load angle across the line is about 25 degrees. In order to increase the load transfer, the operator must first increase the steam input to the turbine by adjusting the governor set point. This causes the rotor to accelerate and so advance the angle of voltage, V1. This now increases the power angle across the line and so increases the load transfer. After a brief oscillation, the governor settles down to its new position with the power angle now at, say, 45 degrees. What would be the situation if we had two identical transmission lines connected between the same buses instead of one? Now, the reactance between each end of the line is divided by 2, and therefore the transfer capability has been doubled for each particular angle of displacement. A new power angle curve can be drawn to represent this condition. On the curve, we can see that for every power transfer angle, the transfer capability has been doubled. For any particular value of load transfer, the load angle required is much less. Also, for any change in load, the required change in power angle is also much smaller. This means that with two lines in service, the operating point is a long way from the 90-degree limit of stability. It is apparent that this connection is more able to withstand fluctuations and remain stable than the single line connection. And for this reason, care must be taken when removing a line from service. In this example, we have generation and load at each end of the transmission circuit. At bus 1, the generation is 8,000 megawatts, while the load is 7,200 megawatts. The remaining 800 megawatts flow across the connection. That is 400 megawatts in each line. And this supplies the load at bus 2. 2,000 megawatts are supplied from the generator at bus 2 to feed a load of 2,800 megawatts. This curve shows the situation with the two lines in service. In order to transfer the 800 megawatts across the transmission circuit, the voltage at bus 1 must be approximately 25 degrees ahead of the voltage at bus 2. If one of the lines is switched out of service for maintenance, all of the 800 megawatts will flow across a single line. In order to maintain this same load transfer, the generators feeding bus 1 must advance in phase so that the voltage at bus 1 is now about 60 degrees ahead of the voltage at bus 2. With this large angular displacement, we are already approaching the stability limit of the line. In order to avoid this, the system operator would probably reduce the load transfer before switching the line out of service. But this may not be possible due to the loading around the system. Now, in this precarious situation, any disturbance on the power system, say a loss of load or a loss of power generation, may cause the voltage at V1 to advance further, or perhaps the voltage at V2 to lag such that the load angle between them exceeds 90 degrees. Beyond this point, the load transfer across the line actually decreases, so the generators at bus 1 accelerate in an attempt to increase the load transfer. This in turn increases their angle of lead even farther, so that the power transfer continues to decrease. At this point, the generator rotors are advancing on those at bus 2. When the rotor passes the 180-degree mark, it's now approaching V2 again, so it can be considered to be lagging. It is trying to catch up to V2. But look what's happening to the power curve. Once the voltage displacement falls beyond 180 degrees, the power flow along the line reverses. Bus 2 is now feeding bus 1. The power flow in this direction is trying to assist the generator rotor at bus 1 to catch up. This is instability. The reversal of power flow in this line will probably create large disturbances on other parts of the system. Hopefully, the generators at bus 1 will pull into phase and remain in phase as they recover their original position. However, experience tells us that this is not likely to happen, and the generator will probably continue to accelerate and remain out of step with the system. This condition is known as slipping a pole and is the symptom of instability. The only remedy is to disconnect the unit from the system and then resynchronize. At this point, let's take a break, and then we'll come back and look at other factors which affect stability. For now, please switch off the tape and review this material in your workbook.